Hello. Welcome to Action Squared channel. In this video we are going to show how to solve the integral of the square root of a single variable quadratic polynomial. Here are the main steps to achieve this goal. Complete the square of a quadratic polynomial inside a square root. Integral of the square root of a quadratic binomial. Integral of the inverse of the square root of a quadratic binomial. Integral of the secant of theta. Integral of the reciprocal of x. Let's cover these steps from bottom to top, as each result is an input to solve the next one. The integral of the reciprocal of x. The integral of the reciprocal of x, or the integral of 1 over x dx, always features in the list of basic integral formulas, and it is equal to the natural log of modulus of x, plus a constant c. But instead of just assuming it is true, let's prove it. One way to prove what is the integral of a function is by checking if the derivative of the supposed integral of the function returns the function itself. Once differentiation and integration are inverse operations according to the fundamental theorem of calculus. So, let's check if natural log of x is the antiderivative of 1 over x by deriving it. The derivative of natural log of x with respect to x is equal to the limit as delta x approaches 0, of log of x plus delta x, minus log of x over delta x. Use the quotient rule of logarithms to convert the difference of logs to the log of the quotient. Next, apply the power rule of logarithms, so that 1 over delta x that is multiplying the log becomes the exponent of its argument. Replace the variable delta x over x by n. When delta x approaches 0, so does n. Changing the variable allows the exponent to be broken in 1 over n and 1 over x. Then, 1 over x can become the term multiplying the log by applying the power rule of logarithms again. As 1 over x does not depend on n, and log is a continuous function in its domain, it is possible to move both of them outside the limit. The expression in the brackets is equal to the irrational number e, base of the natural log. So, as the derivative of the natural log of x is equal to the reciprocal of x, then the integral of the reciprocal of x is equal to natural log of modulus of x, plus a constant c. Note that the result is the natural log of modulus of x, as the log function is defined only for positive values of x. Also note the presence of a constant c to stand for an offset of the function in the solution of indefinite integrals. The integral of secant of theta. To solve this integral, first multiply and divide by secant of theta plus tangent of theta, which is the same of multiplying by 1. By doing so, it's possible to apply the method of variable substitution, with u equals to secant of theta plus tangent of theta, and du equals to secant squared of theta plus secant of theta times tangent of theta, d theta. The integral of secant of theta, d theta, becomes the integral of 1 over u, du. Use the result from the previous step to return to the original variable, which is equal to the log of the modulus of secant of theta plus tangent of theta, plus a constant c. The integral of the inverse of the square root of a quadratic binomial. The strategy to solve this integral is to replace the variable y by something, such that it is possible to cancel out the square root. Remember the Pythagorean identity, secant squared of theta equals to tangent squared of theta plus 1. Applying variable substitution with y equals to k times tangent of theta, and dy equals to k times secant squared of theta, d theta, does the trick. After the appropriate simplifications, what is left is the integral of secant of theta d theta, which was solved in the previous case. Returning to the original variable leads to natural log of modulus of square root of y squared over k squared plus 1, plus y over k, plus a constant c1. After some algebraic manipulations, the constants can be combined into a constant c. Hence, the integral of 1 over square root of y squared plus k squared dy is equal to the natural log of modulus of the square root of y squared plus k squared plus y plus a constant c. The integral of the square root of a quadratic binomial. This integral is a good candidate to be solved using the integration by parts. The formula is integral of u dv is equal to u times v minus integral of v du. In this case, u equals to square root of y squared plus k squared, du equals to y over square root of y squared plus k squared, dy, dv equals to dy, and v equals to y. Thus, the integral of square root of y squared plus k squared, dy, becomes y times square root of y squared plus k squared, minus integral of y squared over square root of y squared plus k squared, dy. Note that the second term is similar to the previous result, apart from the variable y squared in the numerator. To handle that, add and subtract k squared, which is the same of adding 0. Next, decompose this term into the integral of y squared plus k squared over square root of y squared plus k squared, dy, and the integral of k squared over square root of y squared plus k squared, dy. Simplify and combine like terms. Now use the previous result. The solution is equal to 1 over 2 times y times square root of y squared plus k squared times natural log of modulus of square root of y squared plus k squared plus y plus a constant c. Completing the square of a quadratic polynomial inside a square root. The intention is to rearrange the expression of the quadratic polynomial inside the square root to a form that resembles a quadratic binomial, with one part of degree 2 containing the variable term, and the other part without any variable. To achieve this form, extract the coefficient of x squared from the expression by dividing all terms by a, and bring it to the front of the expression. Next, add and subtract b over 2a squared. The first three terms can be expressed as a square of a binomial, corresponding to the part containing the variable term. And the remaining terms can be added together, corresponding to the part without any variable. So, the expression becomes square root of a, that multiplies square root of x plus b over 2a squared, plus 4ac, minus b squared over 4a squared. The integral of the square root of a single variable quadratic polynomial. Let's rewrite the integral using the expression obtained from completing the square step. Now, consider x plus b over 2a equals to y, and 4ac minus b squared over 4a squared equals to k squared, and then apply the result of the integral of the square root of y squared plus k squared, dy. Time to expand the expression and simplify by combining like terms. Some more algebraic rearrangements and simplifications. Combine the constants into a single constant c. Here is the result. The integral of the square root of ax squared plus bx plus c dx is equal to 2ax plus b over 4a times square root of x times ax plus b plus c plus 4ac minus b squared over 8 times square root of a to the power of 3 times natural log of modulus of 2 times square root of a times square root of x times ax plus b plus c plus 2ax plus b plus a constant c. Let me know in the comments if you have a different approach to find this solution. If you like this content, please support us by liking this video, subscribing to our channel, and turning the notifications bell on. Hope to see you in the next video. Thank you.